So today I'm going to talk to you about building good mechanisms with RMG. Um, let's see. In this workshop so far, and in the next day, you'll see a whole heck of a lot about a lot of different tools, how to install them, what they do, how they work, and how to run them properly. But putting this all together and building an accurate chemical kinetic mechanism involves a little bit more than the sum of the component tools. And so originally, Bill added this talk in general to sort of provide a more big picture view of how to using RMG to generate kinetic mechanisms, providing insight into the more messier and more practical parts of the mechanism refinement process and mechanism errors, and also to kind of help improve the way you think about mechanism refinement. Also, more particularly, this talk has a lot of non-trivial recommendations and insights that can potentially save you weeks or not months of work. So there's some important content in this talk, I would say, in this lecture. We're going to talk a little bit, we're going to take a little bit of a step back. We're going to talk about why we're building chemical mechanisms in the first place. What are we trying to do with them? And then we're going to dive a little bit more into the practice of how you actually go through and run the mechanism refinement process and how to think about all the different sources of error in mechanism refinement, and also to talk a little bit about comparisons with experiment. So first, why do we want to build a detailed chemical mechanism? So two sort of systems that you can kind of split things off into and compare is comparing, suppose you ran an experiment and fit some simple model to it, versus generating a detailed chemical kinetic mechanism and simulating it. And for this sort of experimental case, in general, you'll get very accurate results in the particular for the particular thing you ran the experiment for. It can be challenging to imitate the target chemical system. It provides generally a very limited resolution of that system. And doing this tends to be very expensive and very time consuming. In contrast, detailed mechanism simulations are often less accurate, but are much less expensive, much faster. It's generally easier to resolve the exact target system you want, and often provide high resolution information about the system, the concentrations, temperatures, pressures. And in particular, they're far better at extrapolation across a range of conditions than some simple interpolative model you fit a few experimental points to. And this lets us use detailed chemical mechanisms to gain sort of improved understanding of the chemical process, develop design principles for things, discover unobvious chemistry, like fouling and decompositions. And it lets us relatively easily optimize processes, screen possible processes, and simulate cases where it's less practical to run experiments. One of the more common cases for this is in chemical process development in R&D. And you might have some case where you have some proposed possible chemical process that might get proposed in a company, and then the company will fund some small studies to focus on building a chemical mechanism that describes the reactions involved, and some benchtop experiments to validate the process with. These laboratory experiments are usually relatively inexpensive experiments, so they're not going to be that similar to the pilot study, to the real system or the real reactor that you might build or the pilot study. And what you'll do what is done in this process is that you'll develop this detailed model, you'll validate it against these laboratory experiments, and then leverage this detailed model to predict what might happen in a real reactor. And then at this stage, you'll make some argument as to whether you should go forward with this process or not. Is this a good idea based on this detailed model? And if so, then the company might shell out a whole heck of a lot more money to go run a pilot study that looks very similar to the real reactor. And then they'll take this detailed model, use this detailed model to plan what the pilot study is, and then they'll tightly fit the detailed model, or maybe a reduced version of the detailed model, to interpolate the pilot study and the production conditions for the real reactor, and use that and if that's successful, they'll use that to design the real reactor. And there's a couple important considerations here that this sort of system implies, and there are a lot of other applications, but all of them look relatively similar, similar ideas. In particular, often the laboratory experiments that you might be comparing against in a study are very different from the real system or whatever system you're trying to predict. And so we're really interested in these extrapolate and our ability to use these detailed kinetic models to extrapolate beyond where we have these experimental data. So in general, we're not trying to predict the laboratory experiments. We already know what they are. We're trying to predict it some other condition that's very different. But we might use the laboratory experiments to gauge how accurate our detailed model is at this stage, and also to kind of inform like where we should be running calculations within the detailed model. What parts of the detailed model should we be improving? So now to talk a little bit more about mechanism generation in practice. So before you start running RMG, before you touch RMG and start trying to do that, it's important to have a really good grasp of what your results should be. What species or intermediates should be in this model? In particular, what products are you expecting from this reaction? How fast should this reaction be happening? There are a lot of ways to dig around and figure these things out. You can talk to people that are more familiar with your system, read up in the literature on the system, or at least similar systems. There are worse ways to start a literature search. Don't trust LLM general summaries. I've had some very bad experiences with them. And in the long term, you want to build your chemical intuition for all of this and get a feel for if you do this for long enough, you get a pretty good feel for when something's going wrong in a mechanism or something's missing. It's also important to think deeply about what you're trying to do with the model. What are your prediction targets? What are you trying to do with this model? What are you trying to predict? How good an accuracy do you need to predict that with? And knowing these in advance and having these figured out will greatly facilitate your ability to resolve early model generation issues, figure out when something's wrong, and also avoid potentially time-consuming distractions in the model generation process. Now, once you start running RMG, it's important to understand that running RMG alone once will usually not get you to quantitative accuracy for whatever you're interested in. In practice, we're usually going to need to make iterative improvements to converge to accuracy in a workflow, something like this, where we might start. We take the initial RMG database chemical knowledge. We take our system conditions for our system of interest. We run RMG to generate a chemical kinetic mechanism. We simulate it. We analyze it. We run sensitivity analysis. We compare with the experiment and decide on a set of important species and reactions that we want to calculate. We might run quantum chemistry. We'll take those quantum chemistry calculations and integrate them into our chemical knowledge. We might retrain the SIDTs in the database. We might fit new groups to group additivity, etc. We might add reaction libraries and thermal libraries to improve our chemical knowledge. And then we rerun RMG and we get a new mechanism. And when we analyze this mechanism, often we'll get different sensitivities. We'll get a different experimental comparison. And we'll run this process again and gradually converge through these iterations, converge our mechanism to quantitative accuracy. Now, this involves a lot of complex steps. You're probably not going to be an expert in all of these individual steps within this overall workflow, which is why having automation and good tools, which hopefully we're providing to you in this workshop, and also good collaborators can go a long way towards facilitating and making this process a little bit more manageable. However, I would say that all of these are not, well, all of these are important aspects of all of this. I would put some particular emphasis on mechanism simulation and analysis. And being an expert on mechanism simulation and analysis is very helpful in doing this process because it can save you from mistakes that you make in these other parts, which doing well in these other parts won't save you if you've screwed up the mechanism simulation and analysis or other parts of this. But if you understand how the mechanism is working, it's relatively easy to make good guesses about what rate coefficients might be wrong, or how, if the parameters were slightly different, what sort of predictions you might get. And these sorts of questions that can lead you down paths that help you fix problems in the rest of the workflow. And this is particularly important because if you look at these four areas, this is probably the least hot research-wise, but I would say it's the most important in getting a good, accurate mechanism, because it really helps you run this whole workflow properly. Now, our overall simulation might look like something. We might have some set of variables, concentrations, temperature, pressure that we're trying to predict in time. We have some R reactor that we're modeling. And we have our mechanism, this omega, which is our fluxes that come from the mechanism, which is reliant on, which is a function of our state variables and our parameters for that mechanism. And we have some initial condition for our simulation. And our errors in this simulation, which is usually what you're going to be comparing with an experiment, can be broken down into three important error sources. The first is model truncation error, which is errors from reactions and species that are missing from your mechanism that should be in your mechanism. And then there's parameter error, which is associated with errors in your PMEC, errors in the numerical value of your rate coefficients and thermochemical parameters. And lastly, reactor error, which is errors in your representation of your reactor relative to the real reactor you're comparing against. And these roughly correspond to sort of these three different sections of the workflow. So model truncation error, you'll hear a lot more about this in the advanced RMG lecture. You can divide the model truncation error into sort of 4 different types of error. The first two that are probably most important to think about first is internal parameter error and internal reactor error, which are essentially those other errors associated, but propagated into RMG's mechanism generation. If we don't have good parameters inside RMG won't add certain chemistry that it needs to add because the parameters are wrong. And the same if you're with the reactor, the internal reactor error. However, these ones, particularly internal parameter error, is going to usually decrease as you start to improve your parameters in the iteration process. And as you improve your reactor simulations. So in general, these ones are the ones that you want to handle first. So usually you want to handle parameter error first. And these ones will start to go down, and worry about these things a little bit later usually. However, these ones are very independent of those other two, parameter error and reactor error. So missing species and reaction errors occur when chemistry is not added to the model because RMG is unaware that those reactions or species exist. And to handle this, you may need to add new reaction families or library reactions so RMG knows the chemistry. You may need to tweak the species representation. You can often find these reactions and species through literature search and through running quantum chemistry calculations. And lastly is species selection errors, which are is a little bit of a grab bag for chemistry that's not added to the model for all other reasons, which usually we talk about as being for due to RMG's algorithm not selecting them. There's some other additional algorithms within RMG that can improve this that we'll talk a little bit more about in the advanced RMG lecture. But more general things to talk about, in particular, you want to converge your targets in whatever you're trying to predict in RMG, not converge RMG to a specific flux tolerance. So you might have your temptation with RMG might be to use it like you use a lot of other software, where you say, okay, I want it to count the flux within 0.01. And then I converged it out to 0.01. So all the fluxes counted out to 0.01. And you'll learn in the advanced RMG lecture that that's not quite what you might intuitively think it means, converging to a given RMG flux tolerance. And really what you want to do is you want to converge your predictions of your targets with respect to RMG model size, not any of RMG's individual tolerances, because that's what really matters here. You want to stop when your model size isn't improving your predictions of the things that you want to predict. Lastly, it's worth noting that you can, if there are species, if RMG knows what the reactions are, which we're assuming because it's not a missing species or reaction error, if you just add the missing species you think are missing, if you think you know what they are, you can add those into your input file, which will force their inclusion in the model. So next we're going to talk a little bit about parameter error. And it's difficult to talk about parameter error without thinking about parameter sensitivity. You'll hear a little bit more about this in the sensitivity lecture. But So suppose we have some forward rate coefficient KF for some given reaction within our chemical network. Now, it's very intuitive. If we take this forward rate coefficient and we make it arbitrarily small, then the flux going through this reaction will be very, very small. And so it will have relatively little impact on the mechanism. So if we wiggle this KF around, not much is going to happen in the mechanism. So if KF is very, very small, it's not going to be sensitive. And on this plot of this normalized sensitivity of this rate coefficient versus the rate coefficient, you can see over here, this is true. If the rate coefficient is really small, it becomes very insensitive. Now, a little bit less intuitively, if we make KF very large, this also decreases our sensitivity. And the reason for this, so there's two primary reasons, main reasons that rate coefficients are sensitive. One is that you have a sensitive branching. There are a couple different pathways that a flux can travel down, and increasing or decreasing this rate coefficient affects how these fluxes branch. Or it's part of a sequence of reactions and it's rate limiting. It's the slowest reaction step in a sequence, so it's controlling how fast that sequence of reactions runs. Now, if we make KF very, very large, in the branching, it will dominate the branching so much that even if you wiggle it a little bit, it won't affect the branching very much. It won't affect where the flux is going, so the branching won't be sensitive to it. And if it's very, very fast, arbitrarily fast, it won't be rate limiting for any of those subsequences within the reaction network. And so in general, as in most cases, as we increase the rate coefficient to be arbitrarily large, it also becomes insensitive. And so most rate coefficients are really only sensitive in a little small band of values. This also holds for the reverse, although the reverse is also dependent on the equilibrium constant. I'm talking a whole lot about rate coefficients here because it's a little bit easier way to talk about these things. However, thermochemistry is generally much more important than rate coefficients because it's coupled with a whole lot of these KEQs. And also particularly because the thermochemistry in a certain way creates your potential energy surface, and if you have good thermochemistry, it keeps the chemistry sane. I was actually asked in a job interview not that long ago about if I'd rather have perfect rate coefficients for a mechanism or perfect thermochemistry for the mechanism. And the definitive correct answer is always thermochemistry. Now, most rate coefficients, since we've established that most of these rate coefficients are only sensitive in a small band. So most rate coefficients, as you can imagine, are not in that sensitive band. The vast majority of rate coefficients are insensitive, and we only really need to know them within about 3 orders of magnitude because they're pretty far down here. There's a significant minority that are going to be somewhat sensitive. They're going to be close up here to this peak. Their uncertainties are going to put it where they could be very close to the peak, but their real value might not be is maybe farther from the peak. And these ones we need to know with about a factor of 10 to ensure that so that we know for sure that they're not close to the peak, essentially. And then there's usually a handful that are very sensitive. These ones are ones that are close to the peak, and we want to know them as accurately as possible. And there are some cases I've run into where you can get some really extreme sensitivities, some rather insanely sensitive reactions that are very close to this peak. So with that in mind, it's important to sort of have a good grasp of what size our errors are in RMG. So if we look at hydrogen abstraction rate family at 1,000 Kelvin, and we look at our rate rules in SIDT, we can see that roughly the median absolute error factors, so a good idea of like roughly half of our rate coefficients are really well estimated. We're getting these within about a factor of 4. We're doing pretty well. But our 2 sigma error factor, which is are around 3 orders of magnitude. So that's good enough for most of these ones over here. So we do a pretty good job, although if you're dealing with a system that's a little bit different than what RMG is used to, you have less similar training data, of course, your errors can be much larger than this. Now, it's also important to think about the size, how accurate of calculations that you can run for each of these and how accurate our different estimates are. So RMG's gas phase group additivity scheme is about as accurate as a B3 lift calculation. So 2 sigma, this might be about 8 kcal per mole error. However, and you'll hear about this with ARC tomorrow, state of the art for gas phase, you can, without too much difficulty, in most cases, you can get pretty good accuracy. You can get within about 1 kcal per mole, or at least close to 1 kcal per mole. In liquid phase, you're going to do a little bit worse due to handling solvation. But on the surface, things are, as I'll talk about a little bit in Pinta, in that later lecture, things are a lot tougher. You have a lot higher errors on these surfaces, and this process becomes a lot more challenging. Now, another really important aspect of these parameter errors is that they're very sensitive to temperature. So these our rate coefficients and our equilibrium constants are often dominated by errors in the energetics, the activation barrier or the enthalpy of formation. And when you break all of this down, you end up with this error factor of this delta E exponential of delta E over RT. And this makes our errors very significantly temperature dependent. And as a result, if we're running the same accuracy quantum chemistry, our model predictions are going to often be significantly more accurate at higher temperatures than lower temperatures. And if you look over here and we look at a 1 kcal per mole error, you can see that at 300 Kelvin, that gets you within about a factor of 5. But at 1,000 Kelvin, that gets you within about a factor of 1.5. And so you may get significantly better accuracy at if you're modeling at higher temperatures than at lower temperatures. So now talk a little bit more about reactor error. So even if your mechanism is entirely perfect, you're not going to accurately predict your experimental targets if your reactor model is a poor representation of the real reactor you're dealing with. You can also have internal reactor model truncation error if the RMG reactor conditions are too different from the real reactor. And in the more general case, depending if you're dealing with a very large mechanism and a very complex reactor, you may have to make some compromises between both mechanism and reactor complexity to handle this properly. More particularly when you're dealing with these things, it's important to carefully consider your target reactor, your fluxes and your unsimulated system history, and a lot of the different aspects of your reactor. So in this case here, so this is an ignition delay experiments and simulations. So the way these experiments are run is you insert some gas into the cylinder, and then you bring your piston. The piston comes down, squishes it to a specific size, a specific compressed temperature, compressed pressure, and then you simulate until it, and then you wait until it ignites. You wait and see how long it takes for it to explode, essentially. Now, one of the more common ways to model this is you start the simulation from the compressed state. You take the compressed temperature, compressed pressure, and the concentrations that you would have there, and then you simulate that forward and see how long it takes. And that's this dotted line here. And let's look at the green one is probably the easiest to look at here. And you get this dotted line simulation. As you can see here, however, this is not a very good simulation of this ignition delay for methylpropyl ether in this temperature range down here. And this is because the methylpropyl ether is very reactive. And so it actually has chemistry that are occurring during the downstroke of the cylinder. And when we properly modeled, we start the simulation as the piston is coming down, we get this green line, which, as you can see here, matches the experiment very, very well. And this sort of emphasizes the importance of understanding your reactor and making sure you're getting your reactor simulation, you're simulating your reactor well. It's important to test different reactor configurations to sort of check whether adding different potential complexities may make a significant difference. You should also look through literature to see how other people are handling your experiment of interest. So talking a little bit more, so now that we've talked a little bit about all the different sort of error sources, we should walk a little bit through what this whole iterative refinement process looks like and how it kind of works, how to go about this, what stuff you should be thinking about at different times. So in the first iteration, it's important, it doesn't need to be perfect. You want to start simple, start with loose tolerances, make sure you include the important species in the input file or seeds at start, and focus on the first 30, 50 generated species to make sure it's RMG's generating reasonable things that match your expectations. You want to, in particular, be looking for any unusual or unusually important species or very fast rate coefficients. These often indicate issues with thermochemistry. You should check your collision violators file that RMG outputs at the end. You also want to keep an eye out for reactions that you think should be there, that were in your expectations, but you aren't finding them in the RMG mechanism, which may indicate that you need to add a library reaction or add a new reaction family to RMG. Once you've fixed any thermochemical issues with this, and you're getting a generally sane model, you kind of move into this sort of intermediate iteration period. In this case, you're going to be focused on integrating values from calculations in literature for these important and sensitive parameters. Usually want to start with thermochemistry and add kinetics when appropriate, unless you're planning to run all of those, as is often common in surface systems. You want to test different RMG seeds. It's also worth forcing RMG to include species you think should be there, but check and make sure that after you added them, they're still being used in the mechanism. This kind of process can expose some species selection errors. More particularly when you're looking at like properties you're trying to converge, focus on the selectivities first. And then focus more on the reaction timescales and conversion and how long it takes to run the reaction. Now, once you have a qualitatively accurate model and things are kind of coming along, things get a little bit harder in this stage. In this case, often you may have calculated many of the species, most of the sensitive species and reactions, and you're still honing in to try and get as much quantitative accuracy as you can out of this. In these cases, you want to really hone in on key branchings and pathways. And also, it's important to look for reactions that may not be sensitive in your mechanism, in your sensitivities, but might be sensitive if the parameters were a little bit different. And that's a little bit more tricky to look for. But these reactions can make a huge difference. Making sure you calculate these kinds of reactions can make a huge difference. This is also the good stage to sort of keep an eye out for unexpected missing reactions. At this stage, you have somewhat of a stable model. You have some idea what's going on here, and it's worth trying to start making some guesses as to, well, maybe at what kind of reactions might exist that maybe RMG doesn't know about. And also for reactions that might just be really poorly estimated. But you didn't calculate them because they weren't sensitive, but if they were well estimated, might be able to affect, might change your mechanism predictions. So lastly, we're going to talk a little bit about matching experiments. You're not going to be able to eliminate all of the errors in your mechanism simulations, and experiments have errors as well. So your model predictions will often not go through experimental data points. And since you know your parameters have errors, and those are a little bit more straightforward to deal with than the reactor errors and the model truncation errors, you're often going to be tempted to tweak them to force agreement with your experiment to make your plots look nice. And in general, this is really bad. The primary values we kind of talked about at the beginning of this, of your kinetic model, is your ability to extrapolate to new conditions. At the experimental conditions, we already know what the answer is. And additionally, your experimental numbers, while independent of your model, provides you some measure of how accurate your model is. Once you start fitting to that data, the model and experiment aren't independent. You may go through the points, but it doesn't really tell you anything about how accurate your model is. It doesn't mean anything that it goes through the points anymore. And there's an old RMG adage that is farther from the data, closer to the truth. And I did want to be extra clear that it's okay that they don't go through the points. I've been showing these plots. I showed this on the slide that talked about errors. These are actually published plots that we published. And where we properly explain why this particular experiment has this issue at these ranges of temperatures and why these sorts of issues are happening. And it's a pretty well cited paper too. So it's okay that your stuff doesn't go exactly through the points, especially as long as you can explain properly where the error is coming from. However, some of you are probably going to do it anyway. So key things about doing this: be clear and honest about what you did about it. If what you did is embarrassing, don't do it. Don't bury it in the SI. Say what you did. And then more particularly, when you're looking at this, your experimental data usually only has significant leverage over a very limited number of parameters in your mechanism. There are a lot of studies where people fit all of their parameters to experimental data, and this can give you really, really unrealistic rate coefficients and parameters that don't really make sense or unrealistic or violate the collision limit. What you really need to do this properly is you want to look at your target, the uncertainty of your target, and look at the what things are contributing to the sensitivity of your target, which can be approximated by the product of the sensitivities with respect to some parameter I and the uncertainty of that parameter. And you want to target a very limited number, so maybe like one, usually one, maybe two, maybe even three parameters that correspond to the largest terms in the summation that hopefully dominate this value. But in general, it is not recommended that you fit those parameters.